Hello, friends. Well, it seems that James Webb has started to do what was expected of him, to stun astronomers and everyone interested in science. This time, he showed us some really impressive results. According to a new study from February 2023, the new space telescope has found at least 6 galaxies that are close to the Milky Way in terms of their mass. This seems to be no surprise, as the universe is teeming with a variety of galaxies of absolutely any shape and size, but there is a nuance. The space in which astronomers see new galaxies is only 500 million years old after the Big Bang, and that's impossible. If we certainly understand how the universe works correctly, is there something wrong with our theories of galaxy formation, or is it time to worry about the validity of the Big Bang theory? Let's try to figure it out. Using the new James Webb Space Telescope, astronomers were able to plunge into the true early universe for the first time, which has always been hidden from our view. Therefore, researchers were not sure what exactly they could find there. Using the data from the first deep space observations, astronomers confirmed the discovery of the most distant and oldest galaxies known to date, but it seems that their latest discovery really has a chance to be revolutionary. According to a study published on February 22 in the journal Nature, astronomers have discovered 6 candidate galaxies that existed at the dawn of our universe just 5,700 million years after the Big Bang. Of course, the existence of galaxies in such a young cosmos is not surprising. Astronomers expected that the first star clusters should have appeared at the end of the so-called Dark Ages, about 400 million years after the Big Bang. So in a universe that is no more than 700 million years old, astronomers expected to see baby galaxies, i.e. tiny star clusters filled with young, bright stars. These anti-galaxies have just begun to give birth to new stars and have not yet had time to combine to form larger structures. Our galaxy has come a long way before reaching its current size and mass, and this has been facilitated by billions of years of star formation and dozens of collisions with other galaxies that are now part of the Milky Way disk. Therefore, astronomers expected that in such an early universe, galaxies would be about 100 times less massive than the Milky Way, and that's the maximum, but the new study seems to destroy this prediction. It's not just that. Some of the galaxies may have a mass of about 50 billion. That is only half as massive as the Milky Way, and one of them, according to the researchers, has about 100 billion stars in its composition, which is similar to our galaxy, or even bigger than it. And this is just crazy, to quote the authors of the study. If the data is confirmed, it turns out that astronomers have seen galaxies 50 to 100 times more massive than they should have been at that time, which of course contradicts modern ideas about how the universe looked and developed at the very dawn. To begin with, I would like to focus on how such discoveries are made. That is, how exactly do astronomers know that they are seeing primordial galaxies and not, say, a bright red star a few light years away? I should note right away that the most accurate way to determine the distance to the most distant galaxies is to determine their redshift using the spectroscopic method. I will tell you very briefly and as simply as possible, what is the essence of these two terms. Cosmological redshift, which refers to the most distant objects in space, occurs due to the expansion of the universe. As space expands, the waves of magnetic radiation, including visible light, stretch. The waves are simply stretched, and thus increase their length. If we could see the ancient galaxies up close, they would most likely look like bright blue structures emitting ultraviolet and visible light, but because we are too far away from these galaxies, the light from them travels billions of years through space to reach us. At the same time, the universe is expanding, and the waves of light are stretched accordingly, changing their length, and now they look not bright blue but dark red to us. So they are not so easy to see. This shift of light from the visible to the infrared end of the spectrum is called the red shift. The farther away an object is from us, the redder it becomes, i.e., the greater the redshift level. Based on this relationship, astronomers realized that by measuring the redshift of an object, such as the Quasar galaxy, we can determine how far away they are from us. And it turned out that the best way to measure the redshift of distant galaxies is to study the spectra of their light. If you divide the light of galaxies into components, as a triangular prism does, you can learn a lot of information about these galaxies. Astronomers pay attention to these black dashes, the so-called absorption lines, which are actually about the white in the spectrum. They appear because atoms of certain chemical elements absorb a certain wavelength of radiation. In laboratories on Earth, scientists have passed light through various chemical elements and know which features correspond to which elements. So, they look at the spectrum of a distant galaxy and look for familiar absorption lines corresponding to, for example, hydrogen, and observe how much these features have shifted to the red part of the spectrum. So, with the redshift, the absorption lines also shift, so by measuring how much these lines have shifted to the red part of the spectrum, you can determine the exact level of redshift, and thus the distance to the distant galaxy. And once again, this is the best and most accurate way to determine vast cosmic distances, and it helps us understand whether the red spot in the Webb image is really such a distant and ancient object. Unfortunately, this important technique has one major drawback: it is very complicated. Astronomers need to spend a lot of time and effort to obtain spectra of a very limited number of galaxies. And if you need to analyze, for example, images from the James Webb, which can contain tens of thousands of galaxies, this analysis technique can be extremely inefficient. Astronomers simply won't have that much time to check all those points of light. Therefore, they usually use spectroscopy to confirm existing redshift estimates, which they determine in advance using other simpler techniques. It turns out that there is a rather clever trick to finding objects with a high redshift, even without the help of spectroscopy. The trick is that even the brightest stars don't emit much light beyond a certain point in the extreme ultraviolet part of the spectrum. In fact, when you're doing fun things like finding the most distant and oldest galaxies, you expect these galaxies to be very bright because of the intense star formation of young stars. They emit mostly high-energy photons, particularly in the ultraviolet range. But here's the rub: this high-energy light leaving the stars cannot reach us in full. It is prevented from doing so by neutral hydrogen atoms located both in the galaxy itself and in intergalactic space. Some of the high-energy photons emitted by the star are so powerful that they simply knock electrons out of hydrogen, ionizing it. Therefore, the light at certain wavelengths from such galaxies will not reach us, but will be absorbed between stellar or intergalactic hydrogen clouds on the way. As a result, in the emission spectrum of stars, you can observe a rather sharp cut or gap called the Lyman gap, and this gap will correspond to light with a wavelength of 91 nanometers. This is the extreme ultraviolet part of the spectrum. Consequently, ordinary galaxies that contain stars, especially young stars, should have a similar gap in their spectrum. This means, in practice, that we will not see the galaxy at wavelengths in this part of the spectrum, i.e. at shorter wavelengths, and vice versa, we will see its long wavelength radiation. Now the universe is expanding, which means that the light from the most distant galaxies is shifting to the red part of the spectrum. Therefore, the ultraviolet light of young galaxies will reach us in the form of infrared waves. Thus, analyzing the spectra of similar galaxies, we will see that the Lyman gap will also shift from the ultraviolet to the infrared. It turns out that in the visible spectrum, or even more so at shorter wavelengths, such a galaxy will no longer be visible, it will be invisible. In fact, it is not difficult to manufacture simple filters that transmit light only in a narrow range of wavelengths. Such filters, for example, are used in the scientific instruments of the Hubble Space Telescope. And, of course, they are also installed in the James Webb instruments, in particular, in the near-infrared camera. This is the instrument that has been used to discover new galaxies. So some galaxies will be observed through certain filters, and some will not. By changing the filters, astronomers will be able to see which galaxies roughly correspond to which redshift and, accordingly, how far away they are. So, the gray area is the actual modeled spectrum of a distant galaxy. The colored lines are the curves of various filters installed on the Hubble Space Telescope, i.e., violet, blue, green, yellow filters, and so on. And finally, the bottom shows a distant galaxy and how it would look with each filter. Now, as you increase the redshift level, you can see the same Lyman discontinuity in the aspect, and how the galaxy will look through different sets of filters. And at certain levels of redshift, as you can see, For certain filters at short wavelengths, the galaxy becomes simply invisible. Thus, by combining different sets of filters, astronomers can see whether a galaxy is observed or not and determine its redshift accordingly. Thus, it is relatively easy to survey even tens of thousands of galaxies within certain redshift values, and there is no need to face the problems associated with spectroscopic measurements. But of course, this technique is not without its drawbacks. In particular, it is by no means reliable, because galaxies can be very different, and not all of them may have enough ultraviolet radiation to cause the same rupture. In addition, excessive dust in galaxies makes them dimmer, which can lead to inaccuracies in determining the distance. In addition, the presence of other sources of redshift, such as gravitational redshift, will also affect the results of observations. That's why astronomers first identify the most intriguing objects and then verify their chemical composition and distance using more sophisticated but accurate spectral analysis. And that's what the authors of the study did, and it's time for us to get back to it. Using different sets of filters, the researchers observed a total of 42,729 different objects and images obtained as part of a scientific program called cosmic evolution. Using the Lyman discontinuity technique and a similar technique called the Balmer jump, the astronomers discovered 6 candidate galaxies with redshifts ranging from 7.5 to 9. This corresponds to a universe in which 500 to 700 million-year-old galaxies will be considered candidates until James Webb sets his gaze on them again, and this time, using his spectrograph, he will study the spectra of these objects. It is spectroscopy that will provide precise answers to the questions of whether these are really galaxies and how far away they are. Distance estimates will be accurate to within 0.1%. And this is the main thing you need to know about the study: the galaxies have not yet been confirmed. They are still candidates and are just waiting for confirmation of their reality. Because in addition to distance, spectroscopy will also show astronomers what exactly produces all this light in the observed objects, whether they are stars or something more exotic. In particular, in their study, the authors note that their mass estimates may not be entirely correct. The bright objects they found may well be the result of the activity of galactic nuclei. That is, they could be powerful quasars with black holes in their hearts that absorb matter. The superheated gas rotating in the accretion disk heats up to enormous temperatures and radiates huge amounts of energy. The brightness of a quasar can darken the galaxy itself and determine how big it is and how many stars it has. Almost impossible, and as one of the study's authors, in his article for Conversation, notes, James Webb already targeted one of the 6 candidates about a month ago, and spectroscopy revealed that it was indeed an ancient quasar. So, nothing is completely clear yet, and according to the author, it will take another year to investigate the remaining candidates and find out the truth. But even if at least one of the candidates turns out to be a galaxy, it goes beyond our understanding of the universe. Scientists certainly don't know exactly when the first clusters of stars began to form into galaxy embryos. However, as we have already noted, it probably started within the first few hundred million years after the Big Bang. After another 1 to 2 billion years, these early anti-galaxies reached adolescence, i.e., they turned into dwarf galaxies that began to collide with each other to grow to the size of the Milky Way. This is the generally accepted version, but since the discovered galaxy candidates may already have masses comparable to our mature galaxy, this means that either our models of cosmology need to be changed, in particular the Big Bang, or the models of galaxy formation need to be fundamentally revised. However, for now, we can only state that we have a really intriguing discovery today, and the confirmation of these data can cause a real stir in modern science. But if you ask me whether the early data that James Webb has obtained is enough to accuse the Big Bang theory of being wrong, then in my subjective opinion, of course not. It is not enough until James Webb has looked into the open galaxies again, so it is premature to draw any conclusions. All we can say for sure is that James Webb does not let us down. He really reveals to us the universe that no one has ever seen, which may indeed be different from what we imagined. In any case, all the most amazing discoveries are just ahead. Thank you for watching, dear friends. Your kind words and support motivate me to make more and more interesting videos. Don't forget to like and subscribe to our channel to keep up to date with all future videos, because there are many more interesting and exciting things to come. See you on our space journey.